All right, thanks. Thanks a lot for that, Noah. So yeah, I named this presentation Economic Excavator Control Design. I'm Martin, like to work with control of excavators, and it's been really nice to see some other presentations about excavator control and construction control, construction robotics control as well here today. So where do we burn a lot of the resources in our engineering work? Well, we want to make a feature, so we typically start with some research and development for that, spend a lot of time, get it in a good spot for hardware testing, which is like the next sort of bottleneck. We want all the hardware available, take some time to prepare and run the tests, gather data as a result, and so on. And then we can deploy the feature to our customer, and that process is fairly fast. So I didn't list it here. It doesn't take much time to just push it. And then finally, after that, you might think that now the feature is done, nice, but there is still quite some work left, even after it's quote unquote done, and that is the extension and maintenance part. And that cost is going to stick with us as long as we use that feature. So it's an important sink of engineering time. So the core message of this presentation is to try to keep the control as uncomplicated as possible to make it easier to maintain and extend and so on. Simplicity is important in all engineering, and it's emphasized a lot in software development, especially with the agile paradigm, emphasized in the US military, and not only by engineers, but also by Einstein. So this, I think, is a pretty trustworthy group that promotes simplicity. Unfortunately, though, it's often overlooked, especially in my field, control. So I also added an example here of a complicated system. I just Googled spaghetti code, and I found this thing. And we can't see the details because it's tiny and blurry, but we can see that it's hard to maintain and extend something like this. I've written much worse programs myself, but they don't fit on one slide. So I went with this one. Somebody asked me what tool it's done in. It's LabVIEW, but nothing wrong with LabVIEW. You can see that it's kind of complex and messy, and that's actually a good thing about graphical programming. That if you make it too complex, at least that shows early. There are a lot of challenges in robotics in general that everyone here at ICRA is very concerned about. So robot control is, for example, high dimensional, and already there it's more complicated than a lot of control problems, I would say. Then there is the other aspect here that we actually want to control and change the environment, and this was also reported as a big thing by Scale Robotics and Professor Michael Milford as well. So, and this has two aspects. So one is that it entangles the perception and the planning side of things because the environment is changing. The other part is that we deliberately want to change the environment. So we want to control it, but we are only controlling it indirectly. So not only do you need to control the robot, but you also need to control it in such a way, and then in turn, the robot controls the environment. There is more on this list. So it's highly nonlinear, discontinuous, underactuated, high dimensional, and time variant. Underactuated robotics is very interesting itself, and there is a lot of nice course material available for anyone by Professor Ross Tedrake. So I added a link to that here in this slide. And then we have some additional challenges in robotic excavation. So I've compared an excavator to an industrial robot on this slide. So compared to a traditional robot we see in the industry, An excavator is larger, it has lower bandwidth and more inertia, and the actuators are typically hydraulic, and they are, well, more elastic and flexible than what you would see on the industry. So all of this adds to the lower bandwidth. The base is moving, sometimes deliberately as you drive it around, sometimes just by inertia when you move the arm and the body of the excavator is shaking. We have unknown load disturbances, mainly when you're digging. So you cannot model the material that you're digging in perfectly. And so that adds to load disturbances that you have to deal with on the fly. And then you have some interesting coupling. So for example, if I spend a lot of hydraulic pressure on moving one joint on the robot arm, then there is less hydraulic pressure left for the other joints. And we don't really see that in ordinary electrically actuated industrial robots. So here I'm showing a video where we took an excavator and tried to control it like we would on an ordinary industrial robot. And to give you an idea of the performance, I stacked some beer cans on top of each other on the bucket here, and a glass of water on top. So the strategy here is to have pretty tight control loops around the joints. And then once you can control the joint velocities and the joint positions, then you can go one level higher up and just use the kinematic of the excavator arm to move it on a higher level. And this is pretty accurate. No beer was harmed in these experiments. We drank it later though. But as you can see, it's also pretty slow. It's also not robust, unfortunately, as we will see here. So here I'm having the excavator actually do some digging with the same control strategy. We can say that it's still pretty slow as compared to what you would see a human do. You will also see some start and stop behavior right here. And that is the ground braking, which allows us to move forward a tiny bit and then build up some control error, get stuck, and then repeat this process again and again. So even though we had nice balancing performance, we didn't get that nice digging performance compared to a human operator. So let's see if we try to relax this control loop, so we have lower feedback gains instead, and then have the robot dig. Then this movement actually became much more robust, and we could increase the reference velocity. So just asking the robot to please do this faster. The price is that we can no longer balance beer cans as well, because now we will have to accept some position error instead. So should we fight the dynamics of the excavator? The excavator definitely has more dynamics than we used to from the traditional robotic side. In classic robot control, you try to undo these properties of the robots most commonly. So it has some dynamics, but one of the first things we do is to compensate for dynamics. So try to invent some joint torque that takes care of things like inertia, gravity, Coriolis centripetal forces. Once we have done that, then we invent some reference acceleration, for instance, for the tooltip of the robot, and then move it around in a position control style. Another thing we usually do is to undo the robot geometry. And what I mean by that is simply using forward and inverse kinematics. So I have my position references and velocity references in the task space, and then I come up with the corresponding joint configuration. However, and this is sometimes a very good idea. Sometimes I do want to move in a straight line in task space, for example, with the tool, and then this is exactly what you should do. But if that's not the case, then you might be unnecessarily conservative when you do all these steps. So you give away a lot of nice performance. In animals and humans, we see all the time how we make use of the dynamics of ourselves rather than moving our hands in straight lines and starting and stopping and stuff like that. So I call the second version of this compliant robot control because we use the dynamics instead. And geometrically, we tend to try to use joint rotations rather than tooltip movements. So one good example of this is if I'm going to take the excavator bucket out of a trench before dumping, then I could of course try to move the bucket straight up and maybe keep its orientation or something like that. But I could just as well just rotate the boom. And so the boom is like the shoulder of the excavator arm, the joint that's closest to the body of the excavator. And if I only do that, I can do it faster. It's also like much less things that could go wrong with this one-dimensional movement as compared to a 2 or 3-dimensional movement. And of course, there's no benefit for me of moving the bucket in a straight line. So that's a good example where that might be a good idea. All right. So I wanted to soon present my economic design process. But before that, I will present this common design process, which I hope sounds fairly reasonable. So we start with the model of the robot and the environment, and we try to make that as accurately as possible, capture as much as you can in this model. And then we try to control this model in some simulation tool. Then we move the controller to connect it with hardware instead. And we try to move that one. We try to control that one, the hardware, as accurately as possible. And then we verify everything. Hopefully it works. Deploy it. It doesn't sound crazy, I think. Here is what we tend to do at Built Robotics instead, which I call an economic design process. So we start with a very uncomplicated control system. And this is likely not going to work at the first attempt, but it initializes this loop that I called feedback for the feedback design. So we start by evaluating that, and we might be lucky. It might work the first time, and if all the requirements are fulfilled, we should deploy it. It's not trivial to come up with the right requirements for deploying, but if it's a good controller, then of course just use it. Otherwise, if it doesn't work, identify the bottlenecks and increase the limiting complexity. Limiting here is very important. If it doesn't work, should I sample more often? Well, yes, if that's the bottleneck. And then go to step number 2 again. The benefit here is that you avoid making the controller unnecessarily complicated. So you get a simple version of the controller, and then that will be easy to carry with you in the code base throughout through the future of the company. So here I'm sharing 2 cases where we could get away with extremely simple controls. So on the left-hand side, I have used just a bang controller to control the bucket of the excavator. So, and this is only for the joint that rotates the bucket. So when we're going to dump, there is not too much performance requirement. We just want to uncurl the couplers, the bucket as fast as we can. And then when we have done that, when it's uncurled enough, then we want to just stop. If we start abruptly, that's only a good thing because it allows us to shake off some dirt. So it's a perfect use case for bang control. It's just 1 or 2 lines of code. So I'll show you again what that looks like on the left-hand side here. Whoops. All right, let's see here. Here we go. Yeah, that's it. And then on the right-hand side, we use control for moving the tracks to drive around. And the simple thing about this controller is that it's just a static function. So I have a reference velocity, and then I determine the joystick deflection, the thing that controls the tracks. I determine that as just a static mapping from the reference to that. So this one doesn't. This one is just a feed forward structure here, and this is what it looks when it's driving around. So of course, it's not always, it's not every time you can get away with very simple controllers like that. But when you can, I really want to make the point that it's definitely a good idea to benefit from that. And you don't always need a model predictive controller or reinforcement learning if you already know what you want the robot to do. All right, that's it from me. Thanks a lot for listening.